cell phones and laptop audio. Um, so thank you for coming to tonight's San Francisco MySQL meetup. Tonight we have Zardosht, right? Did I get it right? Yes. From TokuTek. He's going to talk to us about indexing. So some really interesting stuff they're doing there, both with their commercial and non-commercial technology. Of course, tonight it's going to be all about the open source stuff. We're keeping Aaron's alive. No sales presentations, of course. Upcoming events, July 12th, we have Facebook coming up. They're going to talk about running large data centers of MySQL and all the fun and hassles of that. So that'll be on July 12th here. Same time, doors open about 6:30, food, and so on. Just take a minute. Does anybody have any announcements for other community events or looking for a job or looking to hire someone? Bueller? Go for it.
All right, so I'm going to be basically reading off something that was sent to me.
Do you have your audio on?
I do not have my audio on.
Testing.
All right, I'm going to be reading off something that was sent to me. Let me just find it. There's been a lot of email today. Okay, so yeah, we have at TokuTek that produces the TokuDB storage engine for MySQL, a position of sales and support engineer. And I'm just going to be reading off the description. We're currently looking for a full-time sales and support engineer to help us handle our growing customer base. Responsibilities include develop and articulate new ways of using MySQL for customer applications to leverage TokuDB's unique benefits and advantages. Run, devise, and publish white papers and blog posts, typical use cases, performance tests, proof of concepts. Work closely with customers to understand and resolve the technical challenges of scaling their infrastructure. Communicate technical issues learned in the field to marketing and engineering to provide new input on new feature implementation and bug diagnosis, to contribute to product roadmap discussion, and I think those are the high order bits. I'll stop at that.
Cool, cool. Anyone else? I always forget to mention CBS Interactive. We're hiring. We're looking for several DBAs, both in MySQL as well as Oracle, and I think we're starting to look for some Cassandra or Hadoop experts as well. So if you know anybody, cbsinteractive.com/careers. Tonight's event sponsored by GameSpot.com and Percona. Percona tonight provided the chicken wings and beverages. GameSpot and CBS Interactive, the facilities and all the fun streaming stuff. Unless there's anything else that I'm forgetting, Aaron? All right, well, I'm going to go ahead and turn it over and we'll get started.
All right, so I'm not used to having a microphone, so just once again, mic check. Everybody can hear me fine? Excellent. So I'm going to use a laser pointer just to point at some things on one of the screens. Just wondering if anyone has a preference. If I point at this one, that one. All right, it's like a win of 2-0 for that one. So can't say I didn't give everyone a fair shot. So all right, so once again, my name is Zardosht Kasheff. I work for TokuTek. We produce the TokuDB storage engine for MySQL. And this talk is understanding indexing without needing to understand data structures. Before I start, I want to once again thank Mike and Erin for having me here. Really appreciate it, and been really looking forward to this for a while. So let's get started. So before we start, we're first going to define a few things. A dictionary is a set of key value pairs, and we're going to assume that you can update a dictionary and query the dictionary. By update, I mean you can write to it, you can insert elements, delete elements, you can change elements. And to query it, you have different types of queries where you can either read exactly one value, just get me a certain value there, or read a range of values in a certain area. So B trees and fractal trees are examples of dictionaries. B-tree is the data structure that's used in many storage engines. Fractal trees is the data structure that's used in TokuDB. And they're examples of dictionaries because mainly what differentiates them from hashes is that they can query ranges, whereas hashes cannot. A table is simply a set of dictionaries. So we have a table here, foo, with 3 columns A, B, and C, and you insert a bunch of data. You can sort of think of it here as one dictionary that has the data here. You see that the data is sorted on the column A, goes from 100 over to 412, and it has all the data associated with it here. The sort order of the dictionary is defined by the key. For the data structures and the storage engines we'll think about, the thing you really need to focus on is that range queries on the sort order are fast. Range queries on any other order is not fast because you don't have the order. It's going to be slow. It's going to require scanning the entire table. And a point query, retrieving a single element out of the table, is also going to be slow. Now, actually, if you're doing only one point query, then it's not going to be slow. But if you have to read a bunch of rows one by one from all over the place, then that's going to be slow. In fact, it's going to be up to 2 orders of magnitude slower than reading the same number if you were just reading it in a range. An index on a table is itself just another dictionary. It has key-value pairs. The key is the index that you define to be the the key is the index that you define, the columns that you define to be the index, and the value in the index is just the primary key. So taking a look at an example, suppose for that table ABC, we altered it and we added a key of just one column of B, then you could sort of think conceptually that the representation of the table is something like this. You have 2 dictionaries. The main dictionary sorted on what you define to be the primary key here that contains all the data. The secondary dictionary, key B, contains just the values of B that you have sorted by that B, and the values are what is the primary key here. So what ends up happening is that these values of A act as a pointer into this dictionary here. So say I want to, say for whatever reason I'm querying the index here, 43, 412, and I want to get the entire row, I use 412 as the row identifier, and I look it up here, and I could get the entire thing. So, by the way, if anybody has any questions at any point, please feel free to ask. So conceptually, this is what the table is going to look like on disk. And what I want to abstract out for this talk here is exactly how on disk the data is represented, whether it's a B tree or a fractal tree. You could just think sort of that the data is sorted this way. Now let's take a look at how some queries would behave, just so we could get a feel for what the performance model is going to be. Suppose I wanted to query the number of elements where A is less than 120. In this case, it's simply just a range query on the main dictionary, really fast, boom, boom, gets the rows consecutively, and returns it. If I want to do select count star where B is greater than 50, here we're going to use the secondary dictionary. We're going to get the rows where B is greater than 50 and just count them up right there and get it. These 2 are examples of range queries that are going to perform very fast. They're going to perform very fast. Now here, on the other hand, is an example of something that would not be a range query. You want to sum up the values of C where B is greater than 50. Well, you can drill down on the rows where B is greater than 50 down here, 56, 56, 92, 202. Those are the instances of B greater than 50. But you don't have the value of C here in order to sum it up. What you end up having to do is, for each of those rows, you get these rows, but for each of these rows, you have to use the identifier, 156 in this case, now 256, to dive into this main dictionary to get the full value. These individual dives are point queries. These are really slow, and these are the things that can tank query performance. So that's the model that we are sort of setting up right here. The first 2 queries were fast. This type of query is slow. Now, given this model, how do we go about designing indexes? Well, the first thing is, why do we even bother with indexes? The whole reason we want to have an index is to speed up some query. Otherwise, the index is useless. So when you're designing indexes, you really want to have some queries in mind. And what you really want to do is pick your most important queries and set up the indexes for those. There's going to be a cost for maintaining indexes, and we'll and we're going to consider them, but what we're going to focus on for this talk here is how do we go about setting up indexes for queries that we care about. And what we're going to do is we're going to have 3 simple rules for designing the good indexes. And once again, we're going to avoid any details on B trees and fractal trees in order to devise these rules. They're interesting and fun, but these rules work with any of these data structures. The only thing we're going to care about is that range queries are fast and point queries are slow. But before we get started with the rules, the first really important rule is that nothing is a hard set rule. There's no absolute rule. Indexing is kind of like a math problem where rules help, tricks help, general rules of thumb help, but every single problem that you have is going to require its own problem-solving analysis. But that said, rules still help a lot. So here are the 3 basic rules that we have. The first one is retrieve less data. Retrieving less data, less bandwidth, less processing, things go faster. Avoid point queries. This is because not all data access is the same. Random access is a lot slower than sequential access. You want to be accessing data sequentially and not randomly. And the third thing is you want to avoid sorting. Group by and order by queries may do post-retrieval work, and indexing can help you avoid this work at query time. So let's start diving into the individual rules. The first rule, retrieve less data. So we're going to set up an example here where we have a table with 1 billion rows and just starting out with no indexes whatsoever. It's going to have 3 columns here, A, B, and C. And a query that we care about, select some C from foo where B is equal to 10 and A is less than 150. The query, sorry, it's just a little weird because I'm used to looking at the screen as opposed to my computer to try to go through this. Yeah, the query has 1,000 rows that match. Now, that means there's only 1,000 rows we care about out of this table of 1 billion rows. Well, what's the query plan if we don't have any indexes? Well, the rows that you care about, where B equals 10 and A is less than 150, can be absolutely anywhere in the table. So without an index, you're actually going to have to scan the entire table row by row to make sure that you found every row where B is 10 and A is less than 150. And the slow execution comes from the fact that you are scanning 1 billion rows just to count 1,000 rows. So how do we go about reducing the data retrieved? We want to design an index focusing on the where clause. In order to get the number of rows that we are analyzing from 1 billion down to something much, much less, you want to drill down on what the where clause states. This defines what the rows the query is interested in, and the other rows are just not important. So here the where clause that we're going to focus and drill down on is where B is equal to 10 and A is less than 150. So let's take a look at a couple of options quickly first. Well, we saw there's an A in the where clause and a B in the where clause. So a couple of obvious options are you use either a key of A or you use a key of B. Now the question is, between these 2 keys, what's better? The answer depends on the selectivity of the index. If there are fewer rows where A is less than 150, then key A is better. If there are fewer rows where B is equal to 10, then key B is better. There's also another option people may be familiar with in MySQL, and it's called, I believe, index merge, where you sort of use both the key of A and the key of B, and you somehow merge the results to get a faster execution plan. I'm actually going to get to this later and explain how that sort of fits with everything. But for now, let's sort of push that to the side. And let's just focus right now on our choices of a key of A or a key of B. The truth is neither of them is really optimal. So suppose you have 200,000 rows where A is less than 150 and 100,000 rows where B is equal to 10. But really, the only data you care about is just 1,000 rows where both of them are true. Then in this case, either of the index is retrieving too much data. This index of B is going to be better than A because 100,000 is better than 200,000, but you don't really want to be using either one. For better performance, the index should instead try to optimize over as many pieces of the where clause as possible. And so what we end up needing is a composite index. So a composite index is going to include both the columns of B and A in your index. We have two options. We can either have a key of A comma B, or we can have a key of B comma A. Question is, which one is better? And this actually gets us to the first really key rule when you're designing indexes, is that you want to pick the column that has the equality check at the beginning. So when you're making a composite index, if you have one that's an equality check and one that is not an equality check, put the equality check at the beginning. So in this case, the key of B comma A is better. And as an example,
that is for any type of index.
Any type of index, the selectivity does not matter. Also, some people think, well, what if I only have 10 unique values for B and I have many more unique values of A? Doesn't matter. B comma A is better. Equality is always better to have at the beginning. And an example of this is, we could take a look here, is you're just drilling down directly. You just jump to the spot, the first instance where B is equal to 5 and A is greater than 150, and A is greater than 150, and you drill down on just the rows you have. It doesn't matter here that there are only two possible values for B, but the values for A are a lot more unique. So what if the where clause does not have an equality, and you have something like where A is greater than 100 and less than 200, and B is greater than 100? In this case, which key is better? Well, let's just go through the four options we have. We have key of A, key of B, and then you have your composite indexes, A comma B and B comma A. Here we get to another key rule. As soon as a column on a composite index is not used for equality, the rest of the composite index is no longer really reducing the data retrieved. So in this case, the key of A comma B is really not much better than just having a key of A. And having a key of B comma A is really not much better than a key of B. Yes, they're corner cases. Once again, these aren't hard dead set rules, but they're going to be corner cases where it's true where A comma B or B comma A is better than the alternatives listed there. But in general, really, this is going to be the same.
How do they compare when you are updating the index?
What do you mean when you're updating?
When you're populating the index, you have a bunch of inserts. You have a key on A and key of A comma B.
Mm-hmm.
How do they compare in speed?
So I believe the question is, how does it compare in speed in populating a key of A versus a key of A comma B? So I work for TokuTek, and for fractal trees, it's really not much of a difference. For B trees, it could be a difference based on the size of your index. So that is a bit of a more involved question, and it sort of goes to the cost of maintaining indexes, which I'll discuss at the end, and we'll definitely get to all of that. But I sort of want to push that off for a little bit. No, it's okay. Please keep asking questions, but and if I don't get to it, please remind me towards the end. But the short answer is, for fractal trees, not much. For B trees, depending on how big it is, it can have quite an impact. So I wanted to just give a quick example of what I was stating in the last slide about how once you have something that is not an equality, the rest of the index really isn't going to be much better. So suppose you had a where clause of B greater than or equal to 5 and A is greater than 150. What ends up happening is you can get rows sneaking in here. Is this having it? Yeah. You can get rows sneaking in here, like 6, 101, where B is greater than 5, but A is not less than 150, that you're going to still end up analyzing. And so this is why and this is what I was talking about, how it's not having the A greater than 150 is really not going to be as much help, because there can be many, many values here where B is equal to 6, which makes it greater than 5, but A is less than 150, and you're still going to be dealing with all of those. So this is what I was sort of getting, and this is showing the first example of how not having an equality clause at the beginning of your composite index is ruining the effectiveness of your composite index as far as reducing the data retrieved goes. Like, there are other reasons which we'll get to later, but for the point of just trying to reduce how much data you're touching and analyzing to answer the query, this is an example of why, of course, you sort of have to imagine a lot more white rows here as opposed to just the one. Like, there can be 10, 20, 100, whatever. But this is an example of why not having that equality clause at the beginning can sort of reduce the effectiveness of your index. So let's take a look at another example. And actually, I was sort of jumping in. So same concept here. You have a where clause of b is equal to 5 and c is equal to 100. Well, from a few slides ago, I think we sort of showed that what you want is an index of b comma c. But for whatever reason, let's just pretend we had a key of BAC as opposed to BC. And this gets us to another key point, is that as soon as you have a column that is really not being used for the where clause, the rest of the index, the rest of the columns after it are not going to be helpful for reducing the amount of data here. So the key of BAC is basically going to be just as good as the key of B because A is not being used in the where clause. And as an example, let's take a look right there. You know, these are the two rows where B is 5 and C is equal to 100, but in between, you're getting these values of A sneaking in that drag with them, basically, values of C that violate this equality clause. And once again, I mean, this is just a slide. I only had space for 8 rows, but in practice, the number of white rows that can come in the middle of this range here can be a lot. So this is why I'm saying, really, having a key of B is pretty much the same as BAC, because you notice, if we just had a key of B, we're analyzing the same 4 rows where B is equal to 5. So let's recap everything with rule 1. You're going to want to create composite indexes that are based on the where clause. And this is really the big one. Place equality comparison columns at the beginning. Make the first non-equality column in the index as selective as possible, because once the first column in a composite index is not used for equality, or it's not used in the where clause, the rest of the composite index is not going to help you reduce the amount of data retrieved. That doesn't mean they're not helpful, and in fact, they can be very helpful as we move on to rule 2. And once again, if anyone has any questions at any point, please feel free to ask. Avoid point queries. So let's go back to an example that I was showing sort of in the intro where we were trying to get a basis for of what the performance model is going to be. We have a table here, ABC. It has a primary key of A and a key of B. And the query that we care about is select some C from foo where B is greater than 50. Once again, the retrieval cost of each row is going to be high because of the random point queries that are going to be done. And once again, this is the animation that we had as a beginning, just a refresher. Each of these point queries that are being done based on your row identifier, which is your primary key, it's at 101 now, each of these point queries is really expensive. And this is what's sort of taking the query. In fact, this is what you want to avoid. When you're doing a query, you do not want these random dives into the hard angle here. You do not want these random dives into this main dictionary. So let's take a look at what we can do. Well, first off, let's just have another query plan. Suppose instead of using the secondary index of B, we scan the primary table. We actually use the key of A and say, you know what? I'm not going to be selective all. I'm just going to read through everything. How does that do? So this actually brings a bit of a surprising fact about table scans, is that the retrieval cost of each row in a table scan is really cheap. So as far as like the second rule goes, table scans are great because the retrieval cost per row is really low. The problem, of course, is everything we went through in the first row is that you're analyzing way too much data. Yes, the 1 billion rows I'm analyzing is cheap per row, but it's still a billion rows, and you don't want to do that. And in fact, once again, in practice, many billion of these, as opposed to 1,000 of these. So how do we go about avoiding point queries? Well, Instead, why don't we try another index of B comma C? Since we're indexing on B, we're only retrieving the rows we need. That's satisfying the first rule that we had. And since the index has the information about C, it doesn't need to dive into the main dictionary to sum up the values of C. It can just go ahead and do it. So we have no point queries. You drill down on what you want. You have the value of C just happening to be sitting there, and you sum it up. And this sort of goes back to the point that I was saying late in the first rule, where I was like saying, oh, the extra columns aren't helping reduce the data retrieved. The extra columns aren't helping. Doesn't mean the extra columns are not helpful. This is how they're helpful. They help you avoid touching this guy, the main dictionary, in a random order. That's the benefit of having the extra columns. So the key B comma C here is what we call a covering index. I'm sure we've heard of it for MySQL users, when you look at an explain plan, if you ever see using index in the explain plan, that means it's using a covering index. That means, I'm just going to go back here quickly. That means it's using only the data that it's finding in this dictionary. This dictionary is sufficient for satisfying the query. It doesn't have to touch that. Animations. And so we're saying that an index covers a query if it has enough information to answer it without having to touch the main dictionary. So let's take a look at a couple of examples. Select some C from foo where B is less than 100, or select some D from foo where B is less than 100. Well, a key of B comma C covers the first query. BC is a covering index for the first query, but it's not a covering index for the second query because second query has D. This guy doesn't. The opposite holds true for the index of BD. BD covers the second query. It doesn't cover the first query. So BD will perform really well for this guy, won't perform that well for that guy. Because this query needs C, this key does not have C. The key of BCD is a covering index for both. So now you can sort of see an example of, oh, I'm only caring about where B is. If I'm focusing on the where clause, I only care about the column B, but you're seeing that you have a key here of BCD where I'm throwing in 2 extra fields and not making these queries that I care about a lot faster. So how to build a covering index. You want to add every field from the select, not just the where clause. And in working with customers, this is a common mistake I've seen time after time after time again, is that for an example of this query, select CD from foo where A is equal to 10 and B is equal to 100. And the mistake people make is they basically just focus on the first rule. They just zoom in on the where clause. And it's a smart thing to do, you know, reduce the amount of data retrieved, just zoom in on the where clause. What's in my where clause? AB, that's the index I need. I'm going to use A comma B. The problem is you still need the values of C comma D, and retrieving these values is incurring the point queries, and this is what's going to make your query slower than necessary. Now, obviously, if your overall table is really, really, really big, 1 billion rows, the amount of data you're retrieving, you know, the number of rows where A is equal to 10 and B is equal to 100 is really small. It's 1,000. Those 1,000 point queries are not going to be, you know, that bad. It's still going to speed up your query by quite a bit, but it's still slower than it needs to be. The correct index you want is A, B, C, D. You want to include all the reference fields, and you place A and B at the beginning in order to satisfy the first rule. So now what if the primary key matches the where clause? So once again, let's take a look at this query where you're summing C from foo where B is greater than 100 and less than 200. But instead, I'm going to alter the schema a little bit. I'm not going to have a primary key on A. I am going to define the primary key to be B followed by an auto increment. I'm placing an auto increment in there because primary keys need to be unique, and the column that you're doing the selection on, B, may not be unique. So you throw in the auto increment there to ensure uniqueness, and you could use that as a primary key. Now what happens if you use the primary key to satisfy this query? Well, it turns out that you're going to be doing a range query on the primary dictionary, And because the primary dictionary already has all the information you need, once again, remember, the primary dictionary has like everything. It has all your columns. Only one dictionary is being accessed, and it's being accessed in sequential order. And this is really fast. So the primary key covers all the queries. So if your sort order matches the where clause for the primary key, your problems become solved. And in fact, and caveat here for MySQL, this is referring to NODB, where with NODB, the primary key stores all the data. With MyISAM, it's different. They don't do that. But so, sorry, back to this is, like if you're doing a selection on the primary key, that's going to be fast. But what if the primary key doesn't match the where clause? Ideally, it would be really great if you could just declare your secondary indexes to carry all the fields. And here I'm going to get into what, as far as I know, is a unique feature to TokuDB, the storage engine that I develop, is that TokuDB is the exception. It allows you to declare secondary indexes that carry all your fields, and to do so, you can declare it as clustering. So did that make sense of what I'm defining a clustering index to be? A clustering index is going to just carry all your fields with it, and as a result, it's going to cover all your queries, just like the primary key. So you can take the benefit that the primary key provides you of making range queries on the primary key fast, no matter what the select clause is you can take it and apply it to other secondary indexes. So let's take a look at how clustering indexes would be used in action. Suppose I have a query workload where the first one I want to select sum of C from foo where B is less than 100. Another I want to sum D where B is greater than 200. C and E where from foo where B is equal to 1,000. You notice, if all I care about is the first rule, and I'm not caring about this range queries versus point queries thing, I could just take a look at my where clauses and be like, ooh, key of B. This is easy. Yes?
Question. What's the point of creating an index if it has all the fields in the table?
The point is that you get another sort order on the data. Okay. So sorry, the question was, I ought to repeat the question. The question was, what is the point of creating a secondary index if it maintains all the fields in the table? And the answer is that the big benefit you're getting from the index is getting a sort of the data. So back to this quick list. So let's take a look. So once again, if clustering keys didn't exist, what would we do? All right, well, if I want to cover the first query, I use a key of BC. If I want to cover the second query, I use BD. If I want to cover the third query, I use B, C, E, and O. That's going to cover the first query as well. And if I want to cover all the queries, because I don't want all these really, really similar indexes, I use B, C, D, E.
And what's the primary key for this table?
Doesn't matter.
But it's different than B.
It's different than B. It doesn't start with B. The primary, we can assume a primary. So the question was, what's the primary key for this table? Doesn't matter. We could say the primary key is A. We could say it's some random column, but the primary key is not related to any of the columns that we're seeing in any of these queries. So the point I'm trying to drive here is that if you really want to eliminate point queries and you want to get everything to be a range query, you got to end up doing a lot more analysis than if you didn't care about point queries and range queries. But point queries are slow. You ought to care about them. So trying to figure out what set of indexes to use for this is a pain. Now, if I just had a clustering key, I define a clustering key of B, and I'm done. That's it. So a clustering key, the big benefit practically of using a clustering key is that it lets you just basically focus on the where clause. It'll automatically eliminate the point queries for you, make your queries fast, and you don't have to worry, and you can just sort of focus on what the first rule is. It sort of just takes the second rule and shoves it to the side. So now I want to go back to what I mentioned. I mentioned something called an index merge when I was discussing the first rule. I want to bring that back and sort of see how it fits in with everything that we have so far. So once again, we had a table foo ABC, no indexes to start off with. the query we care about, select some C from foo where B is equal to 10 and A is less than 150. And once again, just to give an idea of what the selectivity of the fields are, 200,000 rows where A is less than 150, 100,000 where B is equal to 10, and 1,000 that are both, where B is equal to 10 and A is less than 150. So what if we used key of A and key of B and we merge the results? This is what an index merge does. What does this do? Well, the first thing it does is it scans the 200,000 rows in key of A where A is less than 150, and separately scans the 100,000 in B where B is equal to 10. And out of these scans, it identifies the row identifiers, which in our case would be the primary keys for each of those cases, and it merges the results to find the 1,000 row identifiers that we care about. It gets the 1,000 row identifiers, and then it does the point queries with the 1,000 row identifiers to retrieve C. So let's try to analyze to see how this is doing. Well, it reduces the number of rows you're scanning compared to no index. It's doing 200,000 in one, 100,000 in another. It can greatly reduce the number of point queries that you're doing. The more exclusive the two sets are, the fewer number of elements that are in your union, the fewer results in fewer point queries. In this case, it took 200,000 rows, 100,000 rows, and out of that, it basically reduced the point queries down to 1,000. But it doesn't totally eliminate the point queries out of the system. So instead, suppose you just had a clustering key on A. Well, in this case, I'm just going to scan the key of A for the 200,000 rows where A is less than 150. Because the clustering key already has all the information you care about, you're going to scan the resulting rows, and you're just going to pick out the ones where B is equal to 10. And out of the 1,000 that you've picked out, you retrieve the C values, and you're done. So what you end up having happen is you just do one scan of 200,000 rows in your clustering index, and you're done. No scans in another index, no merging, no point queries. What's even better is if you apply what we learned in the first rule, and you just make a clustering key of B comma A. Now, I sort of ought to point out that once again, these are rules of thumb, and you can imagine cases where, not everything is like this simple. If your entire row size, if you have a bunch of blobs and your row size is really big, you may not want to have that clustering key of A because then you're just reading a lot of data and whatnot. So they're corner cases, they're exceptions, but hopefully what this gives is just a model for you to be able to think about how these queries are going to be behaving underneath the covers. So to recap, the rule that we have is, I'll say it again, avoid point queries. Make sure your index covers the query by mentioning all the fields in the query, not just those in the where clause, and use clustering indexes if you can. It covers all the queries. It allows you to just focus on the where clause. And a benefit that I've seen is it speeds up more in unforeseen queries. So it really simplifies your database design. Like I was showing all those queries where B is equal where B is equal to 10, B is equal to 200. In a week from now, there might be some other column you want to retrieve based on B. Clustering key will take care of that in 1 week as well. So the third rule I have is avoiding sorting. Sorry, I thought I heard something. Simple selects require no post-processing. So if I do a simple select star from foo where B is equal to 100, you just get the data, you return it to the user. More complex queries, however, may do post-processing. Group by and order by, for example, require sorts of the data. Index selection, because indexes keep the data in sorted order, can avoid this sorting step during query time. So let's take a look at a couple of queries here. And just to simplify it, I've sort of eliminated the where clauses here. So select count C from foo. And you have a second query of select count C from foo, group by B, order by B. So what's the query execution for these two? Well, for the first one, you just do a table scan and you count the rows of C. I mean, not much else to do. For the second one, on the other hand, you have to scan the table, and you write assuming the data is big enough, you write the data to a temporary file. Then you have to sort this temporary file based on B, and you have to rescan the sorted data, counting the rows with C for each unique value of B. And this sorting step that you see in this, well, writing to a temporary file and sorting step can be pretty expensive. So instead, what if we had the key of B comma C? Well, we're adding all the needed fields that we have. So once again, we're not forgetting the first two rules. Adding all the needed fields, we're covering the query, so that's going to make it fast. And by sorting first by B, you're going to avoid the sort during query time, so that makes it fast. So the key take home here is that if you can use the sort index on the group by and order, if you can sort an index based on the group by or order by fields to avoid the sorting, you can really speed up the queries. So now let's try to actually put everything together. We're going to try to put a few simple examples up and see what indexes we'd use. So the first one, select count star from foo where C is equal to 5, group by B. Well, for this one, we're going to want to use a key of C comma B. First, you have C to limit the rows retrieved using the first rule that we had. Then you have the remaining rows sorted by B, and you're avoiding the sort. So CB is just going to do quick range query. It's going to have enough to answer the query. Select sum D from foo where C is equal to 100, group by B. In this case, you have a key of C comma B comma D. First, you have C to limit the rows retrieved using the first rule. Then you have the remaining rows sorted by B to avoid the sort. And then to make sure that the index is covering the query, because you don't want those point queries into the main dictionary, you throw in the column of B, and you have a covering index. Now, unfortunately, sometimes the answer is not as clear-cut as it can be, and the best index is data dependent. So suppose you have a query, select count star from foo, where C is less than 100, group by B. Well, what options do we have? Well, once again, we want to cover the query, so the columns that are being referenced are C and B. So the two options you have are C comma B and B comma C. So let's take a look at what the query plans are for each of these. If I had the key of C comma B, what would be happening? Well, what we get to do is we get to filter the rows where C is less than 100, but we're still going to need to sort the rows based on B. And the reason is that the rows that we're retrieving are not sorted by B. The where clause is not doing an equality check on C, so the values of B are going to be scattered in clumps for different values of C. And sort of one thing that this example is also pointing out is really the value of having your where clauses be equality clauses. Like, if you can make your where clauses equality clauses and not ranges, that just makes index design a whole lot easier. Like, a lot easier. Like, the reason you're sort of in this conundrum to begin with, the reason why, using this index, you're going to need to sort on B is because your where clause is not an equality check. It's a less than. And so your values of B are not sorted. Yes?
Say you have a B where the cardinality is 10 different values.
Mm-hmm.
It makes sense to still have a composite index there?
If you have well, it makes sense to have a composite. So the question is, suppose you have a column of B that has like 10 unique values. So it has pretty low cardinality. I always forget what low and high cardinality, which ends of the spectrum they are. But there are not that many unique values for B. So in that case, then you're still going to be sorting based on the values of B. Maybe your sort goes faster. Sorry, is the question, does it
make sense to have B included in the key or not?
So the question is, does it make sense to have B included in the key? And yes, it does, because you're going to need to get the value of B in order to answer the query. Whether there's 10 unique values, 100, 1,000, you need to know what those values of B are. And if you need to go to the main dictionary to get those values of B, and those values of B are not available in your secondary index, you're going to be paying the cost of point queries. And you don't want to do that. That's slow. So yes, it does make sense. Yes? You're grouping. So the question is that you don't understand why you need the value of b because you just need the count. So what you're what you're counting is you're not counting the number of rows where you're not just counting the number of rows where c is less than 100. You're counting the number of rows where c is less than 100 for each distinct value of b. So for where b is equal to 1, how many c's are less than 100? For b2, how many are less than 100? For b3, and so on and so forth. So yes?
You have another where clause where you say C and C is greater than 90.
Mm-hmm.
Right? So you have 10 distinct values that C could be. Right?
Yes.
So would it make sense to have C equal 90, C equal 91, 92, 93, 94, 95, 96, 97, 98, 99, 100 instead of, so you can always have the equality instead of the range?
So the question is if your where clause is instead of c is less than 100, c is greater than 90, instead of it being just c is less than 100, the range of c is a little more restricted, and it's, c is between 90 and 100. Does it make sense to break it up into c is equal to 90, equal to 91, 92, 93, and so on and so forth? I believe the answer is yes, and I believe MySQL may do that in some cases underneath the covers. That is actually a smart idea that people have had for MySQL, and I don't know if it's implemented in 5.1 or 5.5, but the short answer is yes. That's the way the query should be done. So, but it's good. So once again, we're kind of in this trouble here because C is not an equality clause. So, oops, there we go. Wait, Sorry. Now let's take a look at the query plan for B, C. Well, it's sorted by B, so rule 3 is covered. You don't have to worry about doing the sort. But the rows where C is greater than or equal to 100 are also being processed, so you're not taking advantage of the first rule anymore. So the question of which is better, well, the answer depends on the data. And this sort of gets back to the very first thing I said about there not being any absolute rule, is that everything is really dependent on your own use cases. If you have many rows where C is greater than or equal to 100, saving time by not retrieving these rows is going to help. So you're going to want to use CB. But if there aren't that many rows where C is greater than or equal to 100, then the time to execute is you're going to end up being dominated by the sorting. Or put another way, if there are not that many rows where C is greater than or equal to 100, then who cares if you're processing those rows anywhere? They're just, such a small fraction of the rows you care about anyway that you're better off saving time not doing the sort. So you're going to want to use B, C. So once again, in general, rules of thumb help, but often they just help you think about the queries and the indexes, and they're not just giving you a dead set recipe. So that covers how to design indexes around the queries. So now I just want to take a few minutes to talk about some of the costs of indexing, and this is where we're going to transition into the question Darren had earlier about what if you add more fields, how does it affect the write speed and whatnot. And so let's take a second to talk about the cost, in that the more indexes are not free. Like when you are inserting data, when you're writing data, you got to keep those indexes up to date. So the more indexes you have, the more of an insertion loading you have, and the smaller your max load is going to be. So what are some of the costs of indexing? And here is where I'm also going to get into some of the properties of the TokuDB storage engine for MySQL that, once again, I develop on. Space. An issue is indexes add storage requirements. I spent a good chunk of time discussing the wonders of clustering keys and how, it makes your queries fast, it makes your design simpler, and, you could just, it makes your life a lot easier. Well, clustering keys end up taking space. The options that you have is, well, to use compression, and the TokuDB storage engine actually has fairly aggressive compression. We've seen it compress between 5 to 15 times on TokuDB compared to other engines. Another issue is performance, and here is actually where the difference of a B tree and a Fractal. Yes?
You say use compression, but how many other database engines support compression?
I don't know. I know others do, but we do, and I think other third-party engines do, but I'm not an expert on.
Archive, Infobright.
Sorry, what was that? Archive and
Archive and Infobright.
Infobright for sure.
Infobright doesn't have indexing either.
Yes, but
And Archive is only one.
Yeah.
unique.
but I mean, yeah. But I mean, the thing here is also just like to sort of get across what some of the costs of indexing is, and to sort of display what the mitigations for those are. And so, InnoDB has some compression in 5.5, but I don't exactly know how good it is.
Is the index on the data or on the index? Is the compression on the data or on the index as well?
So the question is the compression on the data or on the indexes as well? And I assume you're asking for TokuDB, and the compression is on everything. It's on the indexes and the data. It's on, or better yet, I should say the compression is on every dictionary that makes up the table. And once again, the dictionaries are the main dictionary and your secondary.
So then I have a question about compression.
Yes?
So if you have a billion row table and many varchars in there, and you have to do a table scan, you have to uncompress that, and that takes time and is a performance hit and possibly a CPU hit, resource hit.
Mm-hmm.
Is that not true?
So the question is that if you, I want to make sure I understand the question, is that if you have to scan a billion rows, or if you have to do any query that is touching disk. So you have to grab lots of rows. Basically, you have to go to disk to do work. And is the cost of decompression, so the cost of decompression is the question, how does that affect the query? The performance? So, okay, so the question is, how does the compression affect the performance? Well, so
Nothing's for free.
no, absolutely nothing's for free. So the trade-off is basically this. Like, if I'm reading 100 megabytes if I need to read 100 megabytes of data to satisfy a query, I can either read 100 megabytes of data off of disk, or I can read the compressed data, 25 megabytes maybe, if you get 4-to-1 compression. If you have a lot of varchars and you have a lot of repeated characters, you might get much better compression. I read 10 megabytes off of disk. Oh no, you still have to uncompress. But so the cost goes from either reading 100 megabytes off of disk in full, or reading 10 megabytes plus decompression. So the short answer is that if done right, the decompression can use all the cores, and you could actually speed that up quite a bit. It's not as though the 100 megabytes is all compressed in one giant chunk, and it can only be decompressed using one CPU. It could be decompressed in little chunks, 1 megabyte chunks, 4 megabyte chunks or something, and each of those can be decompressed in parallel. So the short answer is I believe it's better, and I really ought to have these numbers memorized, but it ought to be faster to read off of disk and decompress, because you could use the CPU, you could use the vast CPU resources you have, than to wait for the disk to read a larger chunk of data. Does that make sense? Yeah, so any other questions about compression? So the next performance issue is writing. So I'm sure as people, and this sort of gets to what Darren was asking about, what are the effects if I have an index on just A versus A comma B? When B trees get really, really large, it's like, and you're doing random insertions into it, your insertion speed, hope she's all right. Okay. Your insertion speed is going to get really slow. So actually, hold on. I'm trying to tie in Darren's earlier question to this. Let me first talk about the properties of a B tree versus a fractal tree, and I'll sort of try to tie it in. So for a really, really large table, the insertions into a B tree can be really slow. So the more indexes you have, the more ad hoc insertions or writes you're going to be doing, the more random insertions you're going to be doing, the slower it's going to be. And that can be a significant drain on the resources of your machine. And a key difference between fractal trees and B trees is that fractal tree indexes is going to be fast for all kinds of indexing, no matter how big it is. It can, like, we've seen cases where it could be up to 20, where B trees are 20 times slower than fractal trees. And so to tie back into the question that was earlier, it's like, well, what if I have an index of A comma B versus an index of A? So one thing I've noticed a lot of people doing is that in order to avoid this insertion cost for indexes, they're playing this game to try to keep the index in memory as much as possible. Keep that index as small as possible. You want keep that index as small as possible so you can get as many insertions into the index before it starts flowing out of memory. Because once you start flowing out of memory, and I could go in depth into this more if you like, but once you start flowing out of memory, your insertions are going to slow, so you really don't want to hit that cliff. And in that case, then it sort of gets the DBAs to start thinking, all right, well, I have a key on A. That's only a 4-byte key. If I make a key of A comma B, that's going to bump it up to 8 bytes. Is it really worth adding that extra column? That's going to make me hit that wall faster. And yeah, for B trees, you got to take that into account. For B trees, you need to really take into account the cost of writing the data as it gets big. For fractal trees, not so much. Fractal trees are designed so that when data gets really big, that the write performance does not degrade as bad. So that covers writes. And the last I want to talk about is range query performance. So everything I sort of started off the talk by saying range queries are fast, point queries are slow, range queries are fast, and whatnot. Keep everything in a range. Well, it really depends on if that property is true and the range query is actually fast. B trees, unfortunately, can get fragmented. For instance, how many people here have had to run optimize table before because they've noticed queries get slow? Well, what's happening is that your index is getting fragmented. And what's happening is that the range query that's occurring on the B tree is really not so much a range query anymore, and you're still getting dominated by seeks. It's not as bad as point queries, because for the point queries, I'm doing a random seek to get one element. For the range query, I'm doing a random seek to get a bunch of elements, but it's still bad enough where things are not running as fast as they should. So when this happens, we say the B tree is getting fragmented. It can happen from deletions. It can happen from random insertions on a secondary index that has a lot of that has basically randomly distributed data. And B trees get pretty slow. Fractal trees, well, they don't fragment, so we don't have to worry about that. And that summarizes some of the costs that come associated with indexing. So thanks a lot for having me present this. If you have any questions, any thoughts or feedback, yes?
I still don't know what a fractal
I will gladly get into
So,
I will gladly get into.
Would you like me to bring it over?
I will gladly get into fractal indexes. I just want to give my information here, at least for those interested in just the indexes around the query stuff. This presentation is online. If you have any questions, any thoughts, any feedbacks, what's clear, what's not clear, what you like more elaboration on, please, please, please email me. I'd love to hear it. And otherwise, thank you.
I'm not letting him get off that easy. I'm going to make him diagram this because
right.
I still don't know what a fractal is. But you can leave your computer up with your.
Actually, my notes are up there.
Oh,
my
okay.
chickens.
I forgot to mention one way to think about how the indexes work in Toku, which is online indexing.
Okay. So thank you.
When we're done with this, also we have raffle for books and T-shirts.
Okay, so first off, I want to answer any questions people have on what's been presented so far. Then I will mention what Darren told me I should absolutely mention, and I will. And then I will get into fractal trees and try to demystify some of the bold claims I've been making. So yes.
My question is about when you're creating indexes and whatnot. Do you have any preference on the data type that you will be indexing? Is it always a numerical or integer as shown on your presentation?
So the question is, when you're creating indexes, do we have any preferences on the data type? And the answer is no. As long as an equality check is an equality check and a range check is a range check, you should be good to go. So you can have You could do range checks on varchars. You know, I want to get every last name that starts with the letter K. That's a range check, and that should work. I want to find everybody that has the last name of Smith, and I want to, you know, find out how much they've spent at Amazon. That should be fine. Or, you know, I want to get what an IP address or a user ID has been doing. So the answer is no. The key is that you could do range checks and you can do equality checks, and all the analysis holds. Yes?
How do indexes play when you're doing joins?
How do indexes play when you're doing joins? So that is a complicated enough question that I did not attack it in this presentation. So the short answer is it throws a wrinkle into the execution plan, sort of the way that group bys and order bys threw a wrinkle into the execution plan that you saw at times. So the short answer is it makes the rules a little more complicated enough that I wasn't able to just summarize it. But the idea is like, what you want to do, so sort of what you want to do for indexes, there's sort of three things. What I presented was only two things, but you mentioned a third one. One is what your filter is, and that's sort of like your where clause. Like, out of the big table, what are the few rows that I care about? The second is, you know, what's the sort order that do I care about grouping or ordering it? You know, and the third is, do I care about joining it on some other order with another table? So, and for each of these, you sort of want to think about, all right, in what order am I going to be doing these things in? And then you sort of do your index around that. It's just really easy if like your filter is so, you know, selective that you're just getting a little bit that you could just always, you know, clustering key, focus on the filter, you're done. Sometimes it's not that simple, but you know, you sort of think, okay. And really what you want to do is you sort of want to think, and I find it challenging a lot of times, is you want to try to think, okay, how is the query going to execute? Is it first going to filter the rows? Then is it going to join it with this other table? And then is it going to, after the join, when it gets the result set, is it going to do its sorting and grouping by? And based on that, you sort of think, okay, well, I know after my filter and join, there are not going to be that many rows. Like, you know, it's going to be just a handful. So I'm not going to worry about optimizing based on the group by. Or another thing you might think is like, all right, I am joining on a really small table. This small table fits completely in memory. So I'm not going to worry so much about the cost of the join. I'm going to worry about the other part. I'm going to worry about the other parts. So really, although I'm making this short answer as long as possible, the short answer is you sort of try to figure out, you know, how the query is going to execute, you know, what plan it should take, and you design your index surrounded around that. And I saw other hands go up. Yes.
From this presentation, there seems to be no disadvantages to fractal.
Are there any known so the question is, based on this presentation, are there any known disadvantages to a fractal tree? So, I can't tell if that's a really easy question or a really hard one. So the question is, why don't other people use sort? So let me get into fractal trees a little bit, sort of like demystify it, and we can sort of explain the strengths and it'll sort of see the strengths and weaknesses, and I can point to, you know, and you can point to, okay, you know, like the short answer is there are places that we haven't optimized, that aren't optimized fully yet. So, any other questions? Yes.
Getting back to the example where B was either greater than 90 or less than 100,
Mm-hmm.
I still understand why it would make sense to do 10 equality comparisons there instead of 2 range checks.
Or what about just a between function?
Yeah. So, okay, I ought to think about this a little. I ought to think about.
Aren't you still selecting the same consecutive sorted amount of data?
Yeah. So I could have been wrong with my earlier. Let me just think about this for a second. The key is that, yeah. So I think I had to take back my original answer. Is that what you want to do is you want to like find the data you care about, and you want it to already be sorted by B. So sorry, let me repeat the question. The question was like, there was an earlier question about, let me see if I could find the slide quickly. I believe this was it, right? Yeah, so this was the example where for this query, instead if the query where the where clause was C is less than 100, was it between 90 and 100, would it be better to do 10 equality checks? I think I said yes, and I think I was mistaken because the idea is that when you're reading the data, you want it to already be sorted by B, so you can just avoid the sort. And if you're doing it one by one, it's still the overall data is still not going to be sorted by B, so there's still going to be a sort that's going to happen afterwards. So I made it. So yeah, you're right.
Will you just execute this query 10 times pretty much? So each execution will have sorted by B, but we need to do it 10 times.
But you still need to group the final results together.
Data again. If your sort is huge, it may be beneficial. But if like you have not 10 rows actually.
Sorry. So.
Probably will depend on data again.
Well, yeah, that is the short answer. That everything depends on the data, but. So I have to admit, I don't think I quite understood the.
So if you, instead of saying C between 90 and 100, you'll say C equal to 90, or C equal to 91, or C equal to 92. You pretty much execute separate query for each of these equals, right?
Yes, but you still need to merge all those results together.
Yeah,
so okay,
yeah.
so let's go back to the question. So let's just make it a simpler example where instead of C is between 90 and 100, let's just say C is equal to 100 or it's equal to 99. What do we have to do in that case? All right, you run the query for C is equal to 99, and it's got a bunch of counts for a bunch of distinct B's. Then you have to run the query where C is equal to 100, and it's got a bunch of counts for each distinct B's. Then for each of these two sets of counts, you're going to have to merge the results together. You know, if the count for, B is equal to 30 is 10 here, and the count for B is equal to 30 is 20 here, you need to add them up to get a final. I forgot the two numbers I said. Huh? Or no, for the values of B that I said. If the values, if you have 20 for a value of B here, you have 10 for a value there, you got to add it up and put 30 in your final result set. Does that make sense?
Yes.
You got to do, and so what you're going to have to end up doing for 90 to 100 is you're going to have to end up, all right, I have a B is equal to 10 here. Any 10s here? Any 10s here? 10, no. You got to do some merging algorithm, and my merging skills are not, I'm probably not remembering the most efficient merges, and on top of that, even if I knew the most efficient merges, I don't know if necessarily MySQL implements them.
The best way is to do an explain extended on MySQL and see how it does it itself.
Yeah, and then reading something online to interpret that.
Yeah.
Sending an email. What does this mean? So, any other questions on? Whoa, there we go. Any other questions on queries and indexing? Yes.
Sort of unrelated, but do you have any thoughts on geospatial indexes that you're always doing inequalities?
No, I do not. I'm not familiar enough with geospatial indexes to comment. Anybody else? Okay, so I believe there's a request to try to demystify fractal trees a little bit. So I'm going to unplug this, and I am going to bring up my notes. So I think the best way to sort of demystify fractal trees and also give an idea for how TokuDB, a storage engine that uses fractal trees, should be expected to behave. I think the best way the way that I'm going to try to go about this is first I'm going to talk a little bit about B trees, explain what are some of the benefits of the B trees, what are some of the drawbacks of B trees, try to show why you see the pain that you see for B trees, like why do you run optimized table, why do your indexes get fragmented, why do your insertions get really, really slow, and from there I'm going to go, and then from there sort of contrast it to what fractal trees do, and you can see how fractal trees eliminate that pain. So one thing I ought to say straight about fractal trees is that fractal tree is not just going to supercharge anything a B tree does and make it better. It's not just going to, it's not going to give you a big boost in performance no matter what you're doing. What it's going to do is it's going to take the scenarios where a B tree starts failing because a B tree is not designed to do well, and in those scenarios, it's going to perform well. And the way that a fractal tree does this is, the key thing that a fractal tree does is it makes more efficient usage of the disk. So B trees, as I'm going to show show in a bit does horrible things with the disk, and a fractal tree does not. So one of the things to think about as you're using, if you use something like TokuDB, is that if you decide to fire up a machine that has like 32 gigs of RAM, and then you load up a 10 gigabyte InnoDB table and a 10 gigabyte TokuDB table, and you start comparing results, you're not going to see anything, because a fractal tree is not designed to differentiate itself when the entire data is fitting into memory. A fractal tree differentiates itself by how it utilizes your disk resources. So
are they mutual? Sorry, are B-tree and fractal indexes mutually exclusive?
So the question is, are B-trees and fractal trees mutually exclusive? Well, they're different data structures. So the way that a hash is a different data structure than a B-tree. Like a hash tree is a different data structure than a B-tree. So yeah, theoretically, I mean, somebody could come out with a storage engine that has some of the dictionaries be fractal trees and some of them be B-trees, but we don't. All of our dictionaries are fractal trees. So I mean, does that answer your question about exclusive? I'm not sure I answered that.
Depending on the data, would you, if depending on your table and on your queries, if a fractal index makes sense, a B-tree wouldn't, and the opposite way around?
So the question is, if depending on your data, if a fractal tree index makes sense and a B-tree wouldn't, and is it true vice versa? Well, let's actually start demystifying some of this, and hopefully, once the picture is clear, hopefully we can have more targeted questions. So let's see. Yes, I needed a whiteboard for this because I don't have slides. And can we shut this projector off by any chance, please? It's gonna, if possible. If not, I'll deal with it.
Yeah, unfortunately,
I'll deal.
the projector off, it can also turn off the screen.
I'll deal with it. It's okay.
Let's just
No, it's fine.
slide the thing over.
Can we-
It's on wheels.
Don't know if I'll have space. And I'll push the table back a bit. Give this a shot. I'm going to have to sneak behind here to look at my notes maybe at some point. So, all right. So let's just write down a couple of quick properties of. So what are some properties of disks here? So a seek time for a disk is if you want to just go do a random seek. And once again, the reason a point query that I was mentioning is slow is that a point query is incurring, or at least a point query on really large data sets is slow, is that a point query is incurring a disk seek. So a disk seek takes 10 milliseconds. Let's just, I mean, I'm just like eyeballing these things right now. 10 milliseconds. So let's just say you can do about 100 seeks per second. The bandwidth of a disk is, let's just say, 100 megabytes per second. And so that means you could read, if you're just starting off the disk and going off and reading it, you could get about 100 megabytes a second. So what does a B tree look like? A B tree is basically a tree whose branching factor is determined by some block size. So nodes are just a certain size, and you make that some size B here, and you have. By the way, is this clear? Can everyone see? Is everybody? Okay. And somewhere at the bottom here, you have a bunch of nodes of. Let's just say, I believe, does anyone know what InnoDB's block size is? I believe it's 16, but InnoDB's 8, okay? Or let's put it this way: the smaller it is, it's gonna, make it look even worse. So let's just go with. So let's just talk about 16 kilobyte blocks for now, okay? Once again, if the block size is smaller, it could be worse. And so, these, and you have basically these leaf nodes that. And once again, we're talking about really large data sets. The thing that will differentiate fractal trees from B trees are how do B trees and fractal trees behave when your data set is so large. It doesn't get up to 64, does it? I don't think so. I'm just saying like with 60 kilobytes. But the thing that is different with fractal trees and B trees is that your data is so large that your leaf nodes here is residing on disk. All you have in these internal nodes are just basically pivots. So what I want to do here is I want to basically put, let's make a little chart here. Internal node and a leaf node. These are the two types of nodes that you basically have in a tree. Every node's either a leaf node or it's an internal node. And B tree, and you have a fractal tree. So so a B tree for its internal nodes just has a bunch of pivots. And for leaf nodes, it has what I'm going to call small chunks of data. Now, why am I saying that it has small chunks of data? So if you have, let's say, how many people have a MySQL table with a time index? And how many people have, those indexes generally work pretty well, right? You don't run into issues with the time index, and like your insertions just keep trucking along, right? And in fact, and I'm guessing that's rarely a cause for having to optimize a table for any.
It's usually a log, and mine is rarely.
Exactly. So Darren just said it's usually just a log. Now, what do we mean by it's just being a log? So if you have a B tree for when you're first writing data, and if you're writing it sequentially, all of these leaf nodes on disk are basically going to be right very close to each other. And it's not going to matter if this block size is 16 kilobytes, 64 kilobytes, 8 kilobytes. It's probably going to work pretty well if your data is basically being written in that order, one by one by one. But take a case where you do a lot of deletions, or you're creating this table in a very random order. Or theoretically, these blocks don't have to all be next to each other on disk. The leaf nodes, the data that you're retrieving, these are the guys that get touched for your queries. These are the guys, this is where the information has. All of these are basically just arrow signs. They're just directions to get you to where you want to go. But these are the guys that have all the information. If these guys are completely randomly placed on disk, and I want to do a range query, or I need to read a bunch of these blocks, I'm now going at bandwidth speed. What am I doing? I'm doing a 10 millisecond seek, and then I'm reading 16 kilobytes of data. Then I'm going to hop somewhere else to do another 10 millisecond seek, and I'm going to read 16 kilobytes of data. This is, of course, the worst case that I'm talking about. This is when things are just, you jump to another spot, and I'm going to do 16 kilobytes of data. So what is your effective bandwidth here? Well, your effective bandwidth is going to be, you're going to read 16 kilobytes for every 10 milliseconds, or 1.6 megabytes per second. That is way smaller than this one. That is way smaller than what you have here for 100 megabytes. And this is the cause that you get for your fragmentation. Like, things are starting out early on. You're getting something pretty good. You're getting something reasonably close to 100 megabytes per second for your queries, because you just wrote all your data in a clump together. But once things start getting fragmented and put all over the place, and you actually start paying seek costs to hop around to these individual leaf nodes, then your effective bandwidth is just dropping. So does it make sense? And this is actually one piece that hopefully, does it illuminate why you end up having to run optimized tables, and why your query performance, as it gets big, as you do random things, you delete elements, you insert randomly, why you end up having to run optimized table, and why your performance tanks is just the math. 10 millisecond seek, 16 kilobytes of data per seek, 1.6 megabytes per second. That's not a lot. So what a fractal tree has instead is, and the reason I started with the fragmentation, I'm just going to move this over a little bit. The reason I started with the fragmentation is so I could sort of talk about the first big difference between the leaf nodes and the leaf nodes between the B tree and the fractal tree is that a fractal tree has, I'm just going to say, larger chunks of data. So the reason we can say that fractal trees, so if instead of having a 16 kilobyte node, and we're not dealing with compression or anything like that, but instead of having a 16 kilobyte node, suppose you had a 1 megabyte node. So let's see here. So let's see. I'm going to write here, this is sort of just off to the side, the effective bandwidth bandwidth of a B tree was 1.6 megabytes per second. For a fractal tree, let's say you have a 1 megabyte leaf node. You have, well, what's the cost? You have a so to read 1 megabyte of data, you have 10 millisecond seek time. How much does it cost you to read once you actually get to the spot? You have to read that 1 megabyte. That costs you another 10 milliseconds. That's the bandwidth cost. Add that up. You get 20 milliseconds to read 1 megabyte of data. So your effective bandwidth, in the worst case, is going to be 50 megabytes per second. Now, once again, early on, or at least when something's just like a log, if you have a time-based index or you're writing all this sequentially, everybody's living up here. B trees are living up here too. But in the worst case, what we're saying is if you want to try to mess with the layout of a fractal tree as much as you can, and you want to put the nodes in any sort of order that you want, the worst that you're going to do is something that's comparable to your bandwidth. And that's because the nodes are just a lot bigger. So forgetting the other costs of write, just does it make sense why with the bigger nodes, a fractal tree can avoid fragmentation, and that's one of the reasons why a fractal tree has a bigger node, and a B tree fragments down. So hopefully that sort of demystifies some of the fragmentation talk, and you don't have to just sort of take it on faith. Does that make sense? Cool. So now a natural question is, well, gee, why doesn't a B tree end up having a 1 megabyte node? Wouldn't that get rid of its fragmentation issues? And the answer is yes. If you had 1 megabyte nodes and you cared about large range queries for a B tree, that would work. But there are other issues with a B tree. Now, suppose I want to write data into a B tree. Well, let's deal with the case that we sort of know works well. And I sort of saying the case that works well is the time index. And at the end, I'm sort of going to tie like why I even made this indexing talk is because I ran into people loving the time index so much that they violate the rules that I presented in the talk. So if everything is sort of sequential and everything you're sort of writing is out here, your write's going to be pretty good. What ends up happening is you just fill up this leaf node, create another one. Fill up this leaf node, create another one. It's basically just like a log. And so the B tree is working well. In that case, I'm just going to get rid of this because try to keep the integrity of the B tree that I drew. So now instead, suppose the insertion can go anywhere. What does a B tree do? So suppose it wants to go somewhere here. A B tree says, I need to insert down there. Let me search, incur a disk seek, put it there. Need to insert right over here. Search, incur a disk seek over there. Another disk seek over there. If I am incurring a disk seek for pretty much every insertion, I can't do that many disk seeks. Your performance is going to tank. So do people ever see when you have a secondary index and your table is small and then it gets large, it gets large, it gets large, performance, boom, and you go out and you buy more memory. Table grows and grows and grows, boom, like the insertion goes down. Like, is this sounding familiar? What's happening is these leaf nodes are starting to fall out to disk, and your insertions are no longer just going to be an in-memory operation, which is going to be fast. You're going to be going all the way out to the disk, and it's going to read something from disk, update an itty-bitty thing, maybe 10, maybe 20 bytes, maybe 100 bytes, but it's going to read 16 kilobytes of data just to basically do a 100-byte diff. Not worth it. So that would be like the equivalent as I've heard that would be the equivalent of, you order something from Amazon, and someone in Seattle puts your package in a car and delivers it to you. Just you. Then goes all the way back to Seattle and delivers the next package to someone in Texas. And then goes back to Seattle, delivers the next package to New York, and goes back to Florida. That's not very smart. Nobody would ever get these packages. That's what a B tree is doing. For everybody that comes along that, has some data to insert, it is going all the way to New York, San Francisco, Florida, Texas, one by one. And that's why your insertions get slow. A fractal tree doesn't do that. And now we could actually talk about sort of what a fractal tree would look like. So a fractal tree, for its internal nodes, it's also going to have pivots, but it's also going to have buffers. And that's the key distinguishing thing there. So you have, once again, I'm going to draw big blocks. And these blocks are bigger than those blocks, but not really important for the diagram. And so you have a branching factor, you know. Let's just say here. I'm just going to draw these leaf nodes here. You can imagine, you know, the necessary branching that'll, you know. So I am clumsy. So here, like a fractal tree, you see sort of looks the same, but it has the pivots, but what's important is it has these buffers here where information can go. So when you want to go and do a write to a fractal tree, you don't go and just put it immediately down into the leaf. You just put a little message or an instruction, and you just put it right there, and you're done. If I want to insert the value, you know, if I want to insert a certain value somewhere, like I insert the value 100, like 100 comma foo. I don't go all the way search like, all right, is this pivot greater than 100? Down, less, down, down, and go read in a value there. I just say, put a little something right there, and what that is basically is a message that says insert 100 foo. No one's querying yet. Nobody need, like, there's no need for that information to go all the way down yet. No one's querying it or anything. So we're just gonna place it right up there. So
Well, I'm used to those pesky developers that insert and query it right away.
yes.
They can't seem to save it. They read it.
So the
It's
question.
oftentimes within seconds, but sometimes within milliseconds, and sometimes within minutes.
So you're saying that you're used to pesky developers that are used to inserting and querying. So here's the thing with queries. Queries require, if your data is really big and you are querying something random, you're going to go to disk. That's life. But in that case, what's happening is the query is forcing you to go to disk, and then you're just going to be bound by your seeks anyway. So if you're sort of in a workload that...
Can they find it? Because you've put it there, you haven't put it to disk.
So,
where will they find it?
So the question is where, so the question is where will they find it? Because we have not, it's not that we haven't put it, everything that's in memory, like the question was phrased, you've put it here, you haven't put it to disk. This is a node that, you know, just like this node here, if you shut down MySQL, will go to disk. So will this one. So I wouldn't say, you know, you've put it to disk versus in memory. It's you've put it to a location in your data structure.
And it can be retrieved.
Yes, yes. You know, I shut down. So
I don't care if you shut it down.
Yeah.
I have faith
Yes.
that you guys have done that. But what I care is, can I get that information back right away?
Yes. So we'll get into that.
Sometimes it has an auto increment number. So I want the insert null, comma 100 foo.
Yes.
Can I get that back with that ID?
So the question is, can I get null, comma, if I have an auto increment, can you get it back immediately? So the question that's coming is, how do fractal trees behave in a mixed insertion and query workload? And I'll get to that, but before getting to that, let me just explain how in a purely insertion workload the fractal tree behaves. Try to understand why the insertions are faster and don't have the issues that the B trees do. And then I'll bring it back to how it works with the query. So what we do is so when you do a write operation, we don't just go and automatically put it down there. You know, you just sort of put a little message here. And then the next guy that comes along, you know, put it here, 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 here. And only when this thing fills up to capacity, then do you, in bulk, move everything down to the next level. So all the messages here, all the messages here are going to apply, actually, let's just pretend it applies there, but it's actually going to apply based on that pivot, but it's going to apply to a node here. But all these messages here are going to be down here. And what's going to end up happening is these messages sort of get distributed. If it's all random, something like this. So the transition goes, this guy gets full, and say, oh, you guys have got to go. Remove those messages, and it puts it down there. And then whenever these guys finally gets full, one of these guys gets full, that one goes, and you sort of, you know what, let me actually put it in the right one for a change. That one gets full, that one gets full, it comes, and then it makes it to the leaf node. So after the
ground processor is a user process doing message distribution.
Pardon?
Is it background process doing it
Is it
asynchronously, or it's actual user's process writing it?
So is the question, is it a background process or is it a user process? It could be either. I mean, that part, I mean, the key to realize so much is not who's doing it, but it's when it's being done. What is the trigger for it happening? That's the key. For the B tree,
if it's user process, then user process will get unlucky to hit the syntax when this buffer is full, which will need to do a lot of additional work.
But so the question is based on whether it happens during the user process or it happens in the background. So it happens infrequently enough and it's fast enough that it doesn't matter. I'm guessing what you're concerned about is about herky-jerky behavior. Fast, 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 a slowdown during a flush. Fast, 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 a slowdown during a flush. Yes, it's going to be a lot faster putting something just in a buffer than something that incurs a flush. But it's not as though you're going to be suffering any noticeable downtime from the flush. What does a flush take? Well, a flush takes taking a node, reading it in from disk, and that's the thing that I'm not haven't been mentioning is that what the flush is the disk I/O that is being incurred by the system for writes is only happening when a flush of a lot of elements is occurring. So here, what's happening is this guy says, I'm going to move everything down ASAP. I'm going to incur a disk I/O for every single insertion. What this guy is saying is, I am going to incur a disk I/O for only a whole big bunch of insertions. So what ends up happening is, so a way to sort of think of the insertion cost is, if you just imagine this is a constant fraction of the entire node, a very simple fractal tree to think of is just a binary tree where you have block size B, one pivot, 2 pointers, 2 buffers, and you're moving half the data down the time. So basically, the cost of this flush, you're going to be able to do that at bandwidth cost. And the cost of moving any individual element, every individual element is going to be moved basically at bandwidth cost log n times. So you could sort of imagine that your write performance theoretically is roughly within log n of disk bandwidth. Does that make sense? I sort of said that without writing any numbers down, but you could sort of if you want to sort of think of it mathematically, you could do the big O analysis of, all right, if each of these individual flushes can be done at a fraction of bandwidth cost, great. Or you sort of just think of it conceptually, if I'm delivering something to someone, do I pick up a book and drive it all the way to Texas, or do I put a whole bunch of books into a truck and put it at some station in the Midwest? And then a day later, a station in the Midwest gets a whole bunch of books that it's gotten over a series of time and takes it further down, and so on and so forth. That's how the real world works, but it's not how B trees work. And so this is why the write performance of a B tree, this is why the write performance of a fractal tree is so much faster than that of a B tree. So let's sort of get back to what I was talking about originally about small chunks of data versus large chunks of data. Well, B trees want to avoid fragmentation. You say, okay, and I'm doing a lot of range queries on a B tree. I don't want my disk to fragment. I don't want to run optimized table. What if I had 1 megabyte nodes? Well, in that case, instead of like costing you 10 milliseconds to do an insertion, it's costing you 20 now. So you've already taken your super slow insertion hit, the one that's already limited by the number of seeks that you have, that's already just killing you. And because you want these giant blocks, you've already hit that down by another factor of 2. And so now you're just in double the pain you were before. And sort of that's what the B tree is dealing with when it sort of tries to have this trade-off between fragmentation and write performance. The fractal tree doesn't have this trade-off because a fractal tree does not do an I/O unless it's absolutely necessary. It's not going to move one message down all the way to no. It's only going to do it when it has to. And to tie it back to, Tying it back to Aaron's question of, well, what if I have somebody that wants to do read write? Well, a read requires an I/O. And if you need to do the I/O, you need to do the I/O, and you just do it. And as you're doing the I/O, well, as I'm descending down the tree, you could sort of collect the messages that you have, and once you bring in that leaf node, you can just apply the messages, and you say, okay, I've got this deferred work so far. I have this leaf node. Give me a resulting set of, now give me something so I can get the user his answer. And if you're in a read write scenario, and your reads are going to be going to disk, yeah, you're going to be limited by the seeks, but that's your workload. What's not happening is you're not getting a bunch of extra unnecessary I/Os happening from a poor insertion algorithm. And so does it sort of explain why at least a fractal tree doesn't suffer these write issues that a B tree would? Like everything, only big chunks go down, and they all go down together.
Now with the B tree, couldn't you just put a buffer in front of it and then make it more sequential like a time index, because you got a buffer and it organizes it?
So the question is, can you put a buffer in front of the B tree? So can you just put a giant buffer
That's supposedly
like here?
Kona in 5.5 and 5.6 are working on buffering
Mm-hmm.
right to prevent some of this.
So
How's that different then?
So what's different with the buffering is that so as best as I understand, and huge disclaimer, I am not an NODB expert. So this is, as best as I understand it, at least the theory is, the idea behind modifying a B tree for NODB is, let me buffer stuff before it even enters the B tree. But once it enters the B tree, it's doing all those random seeks. What's different here is, as soon as if we want to sort of do the buffer pool algorithm, so to speak, is once this guy fills up, we don't move it down one level. We distribute it all throughout disk wherever it needs to go, and that's a lot more inefficient. So that's the difference, is that when we go, we only move it down as far as it has to go in a way that we can do really fast. This buffer pool sort of says, okay, all you guys are full. Go and do all your individual long seeks necessary and update all these guys down at the leaf level. So that's how I understand the difference. But once again, disclaimer, I'm not an NODB expert.
So you said the fractal indexes have large blocks. Now, if you do need to start just one row, you need to load the whole large block into memory?
So the question is, is that fractal trees have really large blocks, and if you need to retrieve just one row, do you need to load the entirely large row into memory? At the moment, yes. It is something we have not fully, but it's something that we are working to fix. It is right now, it is something that we have just not optimized on. Theoretically, you don't need to read the large block. Because the reads are sort of different than the writes, what you could do instead of, you could say, all right, if I'm doing a read, when I get down to this chunk, I'm not going to read this entire 1 megabyte. I'm going to have enough information to just read the subset that I need. That's the way it should work, and that's the way that it will work soon. It's just it hasn't been done yet, though.
So right now, Fractal is really optimized for sequential I/O, right?
fractal tree indexes are optimized for range queries. They perform well on range queries. They are not optimized for individual point queries. And the reason behind that is sort of what we were saying about in the presentation, is that point queries are slow anyway. Like if you have to do a point query, you have to do a point query. That's life. But like you're better off. But if you need to do like analysis over a range of values, you know.
So yes, your system is not for OLTP pretty much system. This is for
not
OLTP
yet.
system. Okay.
So this is a key distinction. So the distinction I want to make is they said the system is not for OLTP. There are no theoretical reasons why a fractal tree cannot be used for an OLTP system. It's like it's not something that has been optimized yet. It's not something that worked on, but theoretically, it's possible.
Because mostly I hear about TokuTek, Fractal,
Mm-hmm.
as a competitor with InfoBright. That you're both more large volume of data, tend to be time indexed, a lot of sequential writes, and you're fast for huge data
Okay,
sets.
can we go through those one by one, because I really ought to address them. So first part was competitor with, I'll say the competitor with InfoBright at the end. I'm not, once I have to keep giving these disclaimers, I'm not an expert on InfoBright, but really, like, it strikes me that they're separate scenarios. But let's go to the later ones. So
When I was
you said
looking for that
optimize.
solution,
Mhm.
people recommended TokuTek and InfoBright.
What was the solution? So
It was a data warehouse.
Data warehouse, like.
The queries need to be faster than
So let me explain. I don't want to comment on InfoBright because I'm not an expert on them, but I like what TokuDB's strong suit is by taking away the pain of indexing, by taking away the need to run optimized table, by taking away the cliff that you hit when your tables are big, you are able to maintain the indexes you otherwise wouldn't be able to maintain. And as a result, you can get the indexing advantages that were presented in the talk without having the big pain that comes with the indexes. So I sort of think of TokuDB as you actually get to use indexes for real. And so for whatever scenario you're looking for, if indexes would solve if you're thinking, oh, I want to use indexes, but that but doesn't exist with TokuDB. Whereas InfoBright, it's like for, as best as I understand, they're also different scenarios. Huh? They're like, yeah, you know what? I'm not going to comment on InfoBright.
Can you have TokuDB engine and InnoDB on the same instance?
The question is, can you have the TokuDB engine and the InnoDB engine in the same instance? And the answer is yes. Just as you can have the InnoDB and MyISAM in the same instance, along with Archive in the same instance. It's just another storage engine. So
Perhaps if you do a join between stuff.
same those happen if you do a join between MyISAM and InnoDB. It should just work. So sorry, the question was, what happens if you do a join between an InnoDB table and a TokuDB table? And the answer is that it would be just like doing a join between an InnoDB or MyISAM. TokuDB is just implemented at the storage engine layer. So there's some bugs we fixed within MySQL. There's some, we've made some query planner tweaks to get clustering indexes working, and some other stuff that I will get to pretty soon. But it's just to be able to get the storage engine working at the storage engine layer properly. We haven't ripped out any big chunk and made something made something completely new in there.
So why would
But I want-
use InnoDB
sorry, I wanted-
with Toku?
So I wanted to get back to some of the points you were saying. So when you heard about TokuTek, could have sworn you said something about it's good for sequential indexes. It's not that it's
Sequential writes.
sequential. You see that? So you said it's good for sequential writes. So the thing you need to be careful about is when we say it's good for sequential writes, we don't mean the way a B tree is good for sequential writes, the way a time index just works well in a B tree. What it means is that it makes random writes essentially sequential. So that's actually the misconception I want to clear up. It's not that, oh, you take a sequential workload and TokuDB will optimize it. Not true at all. It takes random write workloads, and essentially by this buffering mechanism, you fill, then write, fill, then write. It takes a random workload, and it dramatically improves the write performance of a random workload to something that is like sequential. So it's a big, big key thing that that's a conception that should not be out there. So, and what else? Was there anything else?
Large data sets.
Yes, and the reason that we say for large data sets is this whole analysis is based on you are hitting pain when you go to disk. That's what that's why like this fragmentation is occurring in a B tree. So that's why I wanted to really set up the B tree and its shortcomings and to compare it to the fractal tree. So sort of when we say, oh, you need a large data set, it sort of clicks. Like you need to see a B tree hitting disk here, getting random I/O and really slowing down, and then you compare that to a fractal tree and you see, oh, it's not slowing down. It's trucking along. It's staying good. So when we say you need for the large data sets, what we're really saying, what it's really, well, not what it's really saying, is another way of thinking of it is you need to get to the point where you're seeing InnoDB hurt you. You need to get to the point where InnoDB is becoming unpredictable. It's getting slow. Choose your metaphor. It's running out of gas. It's hitting a wall. It's jumping off a cliff. Whatever. You see that. You don't see that with TokuDB here.
So you can have a gig or 2 gig tables, and you hit that table with any kind of read or write.
Sorry, my leg hurts a little.
InnoDB, that's painful.
A 1 or 2 gig table?
Yeah, I mean when you have. Well,
I mean, a gig or 2 fits in memory. We're talking terabyte maybe?
Yeah. So you have
Okay,
these
yeah.
big tables. I'm thinking
Yes.
rows, really. So
Okay.
let's say I have a billion rows in a table
Mhm.
in MySQL. That can be painful unless it's all ints or something, and it's usually big ints and
So,
ints and decimals.
yeah, we're
and
talking about when a
barcodes.
table flow. We're talking about the case when a table is bigger than memory. This is the pain. This right here is painful. TokuDB does not have that pain for writes. Now,
What about reads?
for reads, for range queries, you don't have that pain. The fragmentation, you don't have that pain. You don't need to run optimized table. Because these blocks are large enough that no matter how these big 1 megabyte blocks are laid out in memory, you can lay them out in whatever random order you want. You're still going to get the really good disk bandwidth performance. The key, as he pointed out, right now is right now a read causes a 1 megabyte write, and it's being addressed really soon.
So, in
Sorry,
this
can you interrupt real quick? We're starting to lose a bunch of people in the room, and I see more people getting tired. Can we do the raffle and then come back to specifics?
Sure.
Is that okay?
That's great.
It's like I'm not going to say
Thank
no.
you very much. So far.